So welcome guys, my name's Damien, I'll be your presenter today. We're going to be going through some topics under the introduction to motion simulation. So it won't be extensive training, but it will give a good overview of the tools and how they might be used. Feel free to ask any questions. I will do my best to answer them as we go, or anything that's left over I will save for the end. So today we are going to be covering a number of topics. I will try and keep the animations as smooth as possible, but do be aware with limited bandwidth they may become a bit jerkier. They will come through fine on the recording. So this will be recorded and uploaded to the MindCAD add-in. So topics we're going to cover, we're going to talk just briefly about what is motion simulation, discussing things such as rigid bodies, degrees of freedom, kinematic and dynamic simulations. We're going to do a really simple introductory case study which is going to introduce the animator interface. So this is not unique to motion, but can also be used in standard SolidWorks for creating animations. However, motion does utilize some of the SolidWorks interface, including the animator interface. We can talk about how to add loads, forces, motors and control them, and we're going to go and use those in a case study of a car jack where we're going to put a load on there and a motor and work out how much torque and power we need to actually lift a car. We're going to extend adding loads, forces and motors and talk about the motion function builder. How do we make more complex inputs? It's a very important part, and we're going to do a third study that's going to demonstrate some of these, and we're going to generate a cam profile for a given input motion. I'm going to discuss contact, do an example of a contact model. In fact, we're going to do two. One of them is going to be our cam we just made, and the other one's going to be a more dynamic system. And we'll talk about those results that we've started again and how to interpret and make sure that they're accurate. Then lastly, the last case study, we will not be building it, we will just be reviewing existing design. It's one I've done for a container lifter, and we'll have a quick review of any further topics. So feel free to ask questions as we go. So what is motion simulation? When we create a new motion simulation tab at the bottom of SolidWorks, we have three types we can use: animation, physical simulation, and motion analysis. So the first two are included with SolidWorks standard. Animation allows us to move and change the visibility and appearance of materials and components in my assemblies and create nice looking animations. The second actually allows them to interact with each other and bounce off, have contact, motors and a few other things, but only gives us realistic looking animations but doesn't actually calculate the forces or contacts or loads or torques or output displacements. And then finally, for SolidWorks Premium customers, motion analysis is included with SolidWorks Premium. There is a events-based motion which is part of Simulation Professional or above. But we won't be talking about that today. So when we talk about motion simulation, we're talking about rigid body systems and mechanisms. So in reality, when we have physical parts and they interact with each other, they will bend and deflect and move. And we can analyze this using SolidWorks simulation using FEA. However, with the motion simulation, all of our parts are considered to be perfectly rigid. So when they interact with each other, it's important to understand this, that they will not bend or deform. And to account for those rigidities, we need to be careful and use the tools to account for them properly. So motion simulation uses the, I believe it still uses the Adams solver. It will solve the equations of motions. It's an iterative solver, so it will take the forces and inertias of your structures and predict the next path and keep iterating until it has calculated the entire path. And we can do two types of systems. A kinematic system where our given path of structural change is given. It's fully constrained by our motors and our degrees of freedom, or our mates, which control our degrees of freedom. In a dynamic system, the movement is determined by the mass and applied forces to the parts, maybe even contact, such as a ball bouncing down a chute, or a Newton, the ball example here, Newton's balls. Okay, so we talked about degrees of freedom. These are important to understand. There are 6 degrees of freedom for any one component. So 3 translational. So the bullet in the example on the right, we can see can displace linearly in X, Y, and Z. 3 translational degrees of freedom. Can also rotate about each of those axes. So a ball falling down, hitting the chute, has all 6 degrees of freedom free. As we add mates, motors, and other components, we remove these degrees of freedom and control the form that they're going. Okay. So fixed parts have all 6 degrees of freedom fixed. Floating parts have some degrees of freedom unconstrained. So let's do our first case study before we get into the details. We're going to use the animator interface, and rather than me looking through here, we're just going to go straight into SOLIDWORKS and have a look. So I have our car jack here, and down the bottom where it says model, we also have a tab called motion study. So it will start with a default motion study. In fact, what's important to note is that when I make a new motion study, wherever I have it zoomed will be my default view. So I'm going to purposely make a new motion study with a horribly zoomed out view. Okay, and even if I zoom in, by default, it keeps snapping back to that original view. That's because we have made a keyframe at that initial view. Okay, we're going to deal with that. So we're going to right click, make a new motion study, and we're going to talk about how to manipulate these keyframes. This is essentially how we work with our motion studies. We can see up here the 3 types we talked about. In this one, we're just going to use simple animation. The top key describes the entire length of our animation, so we can drag it out to 10 seconds, and this can be zoomed in or out as we see fit with these controls. In this case, we're just going to take our example, and we'll see we've modeled this with a number of mates, including a screw mate, some hinge mates, some concentrics, and coincidence. So the way we add geometry to our timeline is to click at a particular place in time. So for example, if I click this orange line at 8 seconds, when I make a change to my model, such as dragging the height upward, we get a new keyframe added because we have automatically create keys. Okay. So when I click calculate now, I get a peculiar looking animation. It didn't do what I want. We'll do that one more time. We can see how it actually goes from the first keyframe through to the last. And we can utilize these filters on my frame to show only things that are moving, or only things that have been animated. Okay, so we have a keyframe here. At this point in time, we can change all manner of different things. For example, all of the mates we put in here, these could be changed. If we had a distance mate, we could just go and change that mate at this point in time. For us, I'm going to create an animation taking the shaft out. So what we need to do is actually turn off the mates that hold it where it is. So we know that screw mate would need to be turned off. So we're going to suppress. And as you can see, we have a off at 8 seconds for the screw mate. As will the last hinge mate. Incidentally, the hinge mate, for those of you who don't know, is actually a combination of both a concentric and coincident, both in the same mate. It allows us to extract loads more quickly. And I believe these last two also need to be suppressed. Okay, so now we've suppressed those mates. If we go to 10 seconds, we'll see we're able to move components. And we're going to move this shaft. We could either just drag it. In our case, we're going to right click and move with the triad. We're going to pull this out. Then when we calculate, just rebuild that and recalculate. Likewise, we can change the appearance of our entities. If I added another 2 seconds to my animation, at this point in time, I could take my shaft, could even filter entities that like the screw rod, and I could say, at this point in time, we are going to change its color. So we can click on the entity, change its color, just the face, make it red. And at the end, we could come in here and we could hide it. So as we can see, we've created the animation where it lifts up, it comes out. I've accidentally done the hide from the beginning. You'll see the keyframe starts from the beginning, but we could drag that out to a point in time that we wanted. Okay, so the last thing we're going to do is just talk about the keyframes you'll see for our camera. If we right click on our camera, we can see it's currently disabled for view key creation, so it won't create any new keys. Now we've undisabled it, we could actually come and change our camera view. And then you'll see that the camera changes from one view to another. Okay, so that's enough with the animator interface. So we're going to use it extensively for our next section, which is going to be talking about loads, forces, motors. So we're going to introduce the rotary motor in this example, which is going to allow to rotate things, as well as creating rotational movement and forces. Also restricts the degrees of freedom. So if we, for example, say a shaft rotates, then we've removed degrees of freedom, so it has to stay on that axis. So it only has a linear degree of freedom left. Okay. Likewise, linear motors allow us to move things in a linear direction. Path mate motors allow us to move them along a path that we've drawn, and we'll see an example later. We can also add forces, and we can even put springs that will add forces to the things they're connected to. So, talking about adding forces, when we add a force to a component, for example, we're going to add one to our jack. The jack moves as we run our simulation. So how does the force update? So when we apply a force, we can choose a reference component, and the force will be tied to what that reference component does. So the first example at the top, we can see we have a fixed reference component, or the assembly origin this might be. So our force, F1, remains horizontal no matter where the arm rotates to, in the same place and position relative to the fixed component. The second example shows the motor, shows the force referencing the rotating components. The force moves with it as it rotates round and round and round. And the third example is more interesting and can be used creatively. We can see that the force is referencing a different component altogether. So that force is spinning at a different rate to the rotating component. It's driven by another one. And this could be another dummy mechanism just to control the way your forces or mechanisms behave, not actually be part of your mechanism at all. So we're going to look at our second case study, which is going to be for the car jack, which is cool. And this one we're going to put a 8,900 Newton load on our car jack. So we're just going to reload this. And we're going to make ourselves a new study. So remembering the first keyframe is what it creates. It's important to zoom it where you want to see it, otherwise you'll be forced to change it. We're going to make a new motion study. This time we're going to use the third entity, and this is motion analysis. This won't be shown unless you have your motion add-in turned on. Okay. We're going to make ours an 8-second animation, and we're going to apply, as we can see on here, we can apply our forces, motors, and we're going to start with a 100 RPM motor. Just note, wherever I'm on my timeline, it's important to remember I'm actually at the beginning now because I haven't changed anything. You'll see how my slider is at the beginning. It's important to leave it where you want to add your changes, and this is something you should get into a habit of doing. We're going to apply a rotary motor. By us choosing a cylindrical component, you'll see how the rotary motor has already been applied to the axis of that cylindrical face. There's no need to have a motor direction defined. But if we wanted to do it somewhere else, we could choose the reference. And we're going to reverse the direction, and we're going to leave it at 100 RPM. Okay. Inside of here we could add additional entities. We could say spin by 360 degrees from 0 to 8 seconds, but we want it to continually spin at 100 RPM. Excellent. So we're going to put on 2 more loads. We're going to put our gravitational load. And you'll see when we're applying gravity, we can choose geometry to specify the direction. Remembering the little green arrow in the bottom right clearly shows us the current direction, and we want it in Y, going straight down. Excellent. So lastly, we're going to put our motor force on. Adding a force allows us to either add action only or action and reaction. So if we were using a force to represent a cylinder, this would be a way to put the forces of that cylinder on the 2 entities that the ends it connects to. In our case, we're going to apply it to a part, and you'll notice it says the application point as well. In our example, if I was to click a vertex such as this one, It would need a direction as well, and I'm going to choose this flat face. We can see our force would be applied to this point, so it would add a moment to my mechanism too. In our case, we're going to use this circular edge. The reason it's important to choose edges sometimes is because circular edges have a center point, which is right in the middle. It's really convenient. Otherwise, a sketch inside of my model would be an appropriate place to apply my load. Okay, because we have a circular edge, it also has an axis for direction, so we don't need to specify the second value. It can save us a lot of time. So again, a constant force of 8,900 newtons, but this could be an oscillating force, or all sorts of different things, which we're going to deal with a little bit later. Okay, so now we have our study. We're going to click calculate, and it has gone from 0 to 8 seconds spinning at RPM. And for me to replay this, I'm going to change the playback speed and just play it from the start, so hopefully it comes up in the GoToMeeting reasonably well, which is great. Okay, so now I've got a study that has an input force and a motor. What I'm really interested in now is some of the outputs. So we're going to use this plot, create results and plots, and this allows us to interrogate and create plots from my model. So the types of things we might be interested in would be displacements, velocities. In our case, we're going to go straight down to our motor torque, which is under forces. I want to know what torque the motor had to endure to create this motion. And you'll see under forces, I have motor torque. And we're going to have magnitude. So what's left to do is choose my motor. If we filter driving, you'll see it has my motor easily selectable. It's highlighted on the screen. As we can see, the required torque for this particular case is about 7.2 Newton meters and reducing as the angle between my scissors changes, which is great. So we're going to go and add one more plot. This one we're going to go straight to momentum, energy and power, and we're going to look for power consumption, again for my motor. And rather than creating a brand new plot, we're actually going to add it to this plot we've just made. And as you can see, we get a plot for both my power at 76 watts and my torque required. And down the bottom we can see we plotted it against time. What happens if we didn't want to do it against time? We want to change that. We can come down and right click on our plot, edit the plot. Rather than doing time, we could choose another quantity altogether under new result. In our case, I want to talk about maybe we want to do the angle. I want to know how much torque based on the angle that's in between, or the vertical distance. So we're going to do ours displacements, linear angular displacement, and we're going to choose two faces, 1, 2. So now we get to see the change based on the angle between my faces, which is great. So what happens when I make some changes to make it a little bit more interesting, because obviously the two curves follow each other. we're going to change the speed of my motor, because as we can see, as we go up to here, the power consumption needed reduces. So at 8 seconds, I'm going to go to my rotary motor. It's important to note I put my marker at the end by dragging it. We're going to edit that rotary motor and make it 200 RPM. So we can see if I hover over these keyframes, at 8 seconds it will be 200 RPM. At 0 seconds, 100 RPM. So it will change from one to the other. So now when I calculate, we can see that it updates and my power consumption has varied, peaking out about 77 watts. Some of these scatters, if we actually just click on this chart, if I can, are just single points. Because we haven't really got a very accurate model, we've only got 25 frames per second at the moment, it's not very smooth. We can change this really quickly under our settings. My motion manager, we can click the cog or the gear and we can up the number of frames per second. In this case, we're going to change it to 100 and recalculate. Okay, a little bit rough, but we can see and extract those loads as it goes through. Other types of things that people may be interested in, what about accounting for friction? Okay, so when we built these models and we've made these screw mates and these hinge mates, we're going to edit one of these. See, in this case, this hinge here clearly shows the two coincident faces and the two concentric faces. They're combined into one, but the analysis tab on my actual mate allows me to create flexibility and also friction, where we can specify a coefficient of friction and we can choose the size of my journal bearing for this particular case. We're going to ignore it in this case and we're going to move on to the next part of the exercise. Okay, so what happens when I don't want to just apply a single RPM or force and I want something more complex? Inside of there we can change those values, and the most flexible way is using the motion function builder. So there are 3 tabs: expression, data points and segments, and we can go through these and create expressions or to change them. So an example would be the step function. So it allows me to create a change from one jump to another one. This last one says segments, which is this bit. I do apologize. So what we need to be aware of though is that when we create a input, for example, we say move from this position to this position, we can use if statements to do that, but we can end up with curves that are very sharp and aren't necessarily what we're after. If I just grab my pen, I can't see it. And pointer pen. So in this case, if we wanted to change the displacement and then rapidly change up to a different displacement, because the geometry has to change so abruptly in direction from one position to another, these are known as singularities, and they make it difficult for the solver to change from one direction to another. For example, if I had an object that was sliding with some frictional forces in one direction, and then instantaneously I moved it back the other way, would have forces acting, and then suddenly they were acting in the complete opposite, and our equations of motions would be thrown into disarray. So to avoid that, what we need to do is slow it down and then reapply it the other way. So we smooth our curves. So in this case, we can see this curve is smoothly changing. The step function allows us to smoothly change these, and that's how it works. And it's important to utilize these functions over the if statements to make sure we have a smooth blended input. Likewise, we can import data from an Excel, from CSV files, and expressions can be done to feed all manner of different things, including step functions. So let's take a look at some examples. We're going to take a look at the CAM generation, which is going to do the same sort of thing. So in this example, we are going to build a cam that's going to allow this cam follower, this blue one, to go up and down in a prescribed motion. In fact, this is the motion that we have here. So we can see we have a text file that describes time from 0 to 3 seconds and describes a linear displacement. So I want the tip of my cam follower to move in this fashion. So this may have been determined from another machine or some other geometry and exported, could have even been exported from motion, or just measured with a DTI. And what I want to do is move linearly to follow this, and then we're going to make a cam that allows that motion to happen. Pretty straightforward. So just reviewing my model, there's only 2 degrees of freedom left. We can see the cam follower is free to move up and down, and the cam shaft is free to rotate round and round. Okay. So we're going to make ourselves a new motion study. And we're going to do exactly that. So we're going to have 3 seconds. We're going to apply a simple rotary motor. And it's going to go clockwise. And we want 1 full rotation. So over 3 seconds, that is 20 RPM. What we could say, I want it to go 360 degrees from 0 to 3 seconds. You'll see when I make changes like this one, you'll see this is actually the change starting at 0 and going to 360 degrees. However, our constant speed has constant speed. So they are quite different in the way they behave, because the distance and oscillating smooths our curves. So for example, if we say oscillating, you'll see it will smooth up and down in a sinusoidal fashion, and it would rotate one way and then the other. In our case, 20 RPM is what we want. So next we're going to add a linear motor, which is going to move my entity up and down. So this time we're going to change that to linear, and we're going to choose a linear face, and we're going to have that going straight down. So rather than me choosing from here, we're going to come down and utilize the data points. And this brings me to my function builder. Just note when I import my data points, these functions can be for, in this case, because it's a linear motor, can be displacement, velocity, or acceleration. So it's really important to set this to the right quantity. Okay, and we're going to import our cam input. Excellent. So you can see those points have been brought in and show me as smooth. In fact, I'm just going to import this other one here. And we're going to do a linear interpolation. So this other profile is just 1, 2, 3, and then back to 0, 3 points. So we can see when we pull this in for my displacement, 1, 2, 3 points, 0, 1, 2, 3. This is my profile. And how do I get a curve to describe? So if I keep these sharp like this, we're going to get discontinuities and solve a problem. So we need to smooth it. So the interpolation allows me to smooth it either with a cubic spline or a Kima spline. And note that it allows me to calculate and estimate the derivatives of displacement. The first derivative being velocity, so we can see this will be the velocity as it goes down and then goes up, goes back up for my component. And the way that we interpolate between these curves affects this. Likewise, the second derivative is acceleration. We can see what level of acceleration it exerts. And finally, the not so commonly used is the next derivative, which is jerk, which is change in acceleration. Okay, so this is what a rider would feel if when they're bashed around in an accident or a poorly defined roller coaster ride. Okay. In our case, we're going to import our cam input. And because we've got lots of points, it doesn't really matter which one we choose. We could just use our linear one if we want, because they're quite smooth as it is. Okay. So let's go ahead and calculate. Let's see if, oh, sorry, I didn't turn it to motion analysis. Make sure we put it on motion analysis. Okay, and we're going to slow this right down to 0.1 and replay. Actually 0.25, because that's really slow. We can see the shaft spinning 360 degrees, and we can also see the movement that we're creating linearly. Okay, so I've moved the two components I want, and I want to create the relationship between them now. So as well as being able to plot displacement as graphs and quantities, inside of here we're allowed to, under displacement, create a trace path that's going to generate a curve. We're going to generate the tip of this entity. And as you can see, we've got a preview of it going up and down. But if we choose a reference part as a second choice, putting it in the same box, for example, where my cam's going to go, it will utilize the second reference. In fact, I'm going to stop, disable playback of view keys so we can look at it, and now we're going to play it. We can see we'll plot it relative to the second component and allows me to generate a curve for my cam. So we're going to pop this into the other file. We're going to right click on our trace path, create a curve, either in a new part, in our case, because our reference part was the part we want to put the curve in, it's the one we're going to choose. And opening that part, we can see we have generated curve 2. And we're just going to utilize that curve If it wasn't completely smooth, you would probably create like a fit spline to make it really nice. In our case, it's pretty good, so we're just going to extrude it to make my cam and hide that curve. Excellent. Let me just check the time. So we're running just a few minutes behind. So we're going to move on nice and quickly. Okay, so the next topic we're going to talk about is, as well as using mates and joining things together with motors, we're going to talk about contact, which is when we have dynamic systems like a ball bouncing, we need to do. So there's two models. The first one, hopefully highly familiar from your days of school physics, the coefficient of restitution. It's a good example was if you're playing snooker with highly elastic balls. You'll see V1 is our input velocity for one ball, and V1 dash is the exit velocity for the same ball, and likewise for V2 for the second ball. So what we can see is that the change in velocity for one ball is equal to the change in velocity of the other times a coefficient. So for a perfectly elastic collision where no energy is lost, the E will be 1. And a perfectly plastic collision where all energy is absorbed by the collision, we would have E equal to 0. Okay, so very simple. However, it does not allow for prolonged contact conditions. So it's only suitable for short impacts such as these. So there's a more complex model that does the same sort of thing called the impact force model, where what happens is when the contact occurs, the contact force is applied to the two faces where they contact based upon a given stiffness. Okay, and the objects are allowed to penetrate into each other, and that elastic stiffness can have an exponent. If it's just linear elastic like a billiard ball, it will be 1. And a damping coefficient allows us to specify in there how much energy is absorbed through damping, through friction, through heat, through noise. Okay, and that can be set to a max penetration. So when we have these impacts, the way it calculates the geometry, it will be working with tessellated geometry. So we can have coarse tessellation, so our impact will be subjective to how well it fits into triangles. If we want a more accurate contact, we should increase that, and the highest level there is a checkbox to allow precise contact. So we're going to take a look at 2 examples, one with the coefficient of restitution, one with the impact model. So in this example we have some Newton balls, okay, and we can see that we have left the rotational degrees of freedom alone, but we've left it in a position that can be reset. And often you'll end up with creating a mate that positions them at a home position so it's quick to get back. In our case, we're going to make a new study, and it's going to be a motion study, and just going to keep it nice and short so it's fast. And we're going to put gravity on in a y direction, and we're going to apply contact. So our contact model allows it to apply either between, we're only going to talk about solid bodies today, but it can be done to curves too. We're going to go 1, 2, 3, 4, 5. We can group them which can have this part can interact with this one, this one, this one, on this one only. So it can make your computational time easier. Okay, so we're going to neglect friction for now, but this can be considered. Remember, there's dynamic friction and static friction. This account allows us to reduce singularities when we have things that are sliding and change direction. We're going to turn it off. And what's very tempting is to go, I've got steel balls or rubber balls. Let's use my materials and it will work out my elastic properties for me. However, our stiffness and our elastic impact forces are not dependent just on material. So we have a sphere hitting another sphere, they will be highly elastic. However, you have a sphere hitting a really widely simply supported thin plate. A thin plate will deform and move much, much more than the sphere. So material is a measure of both geometric stiffness and material stiffness. So it mustn't be used. In fact, I'd encourage you to turn off material and work and understand how to define your own properties. So we're going to use the restitution coefficient, and this one we're going to set to 1 for a perfectly elastic collision. And we're going to calculate. Okay, so let's play that back nice and slow. In fact, I'm going to pop on a cross-section view just so it's nice and easy to see. And we're going to zoom in a little bit and play. Sorry, disable playback of view keys. So we can see the model behaving nearly well. And let's talk about some of the peculiarities that we're seeing here. So first of all, let's take a look at our first impact. As we can see, this impact is allowing the components to penetrate into each other. So this is how it determines those forces. It allows a penetration to occur, subdivides the interfering body and repels it with repelling forces based upon the impact calculation. So if you want to use contact, you must be aware that it will always allow your geometries to interfere with each other. It's a very important fact to know. We'll also see, if I zoom in a little bit, as I go through, I only have very large steps between one frame and another. This is because in my motion study properties, we only have 25 frames per second. So we're going to pump this up to 100. And if you have really high collisions, this could be thousands, maybe 10,000 frames per second. And in here, we'll also see that we have our contact resolution, and we can change the slider to show that different tessellation, or in our case, we're going to use precise contact. And that's all we're going to do. And we're going to recalculate. So it takes a little bit longer and the steps are a little bit smoother. I'm going to take it off the confusing bit at the end. Okay, so let's look at a plastic collision. We're going to right click on our motion study and we're going to copy, or if you're an older version it would say duplicate. And all we're going to do is go to my contact and we're going to change our coefficient to 0.1, which is nearly, it's quite plastic, but it won't absorb all of the energy because that would be quite dull. And we're going to recalculate. and then play. So we'll see a lot of the energy was absorbed plastically, so it won't go as high as the elastic model. Okay, so let's move on and do our second contact model using the impact method, which is more commonly used. And what we're going to do is do ours for this cam. Okay, so we're going to duplicate the study, go copy study. And in this one, we're going to utilize not our linear motor. We're going to right-click and suppress because we don't want it to be prescribed. I want the contact to occur in my model. So we're going to make sure that we have gravity turned on. And we're also going to put in the contact between the two components. We're going to turn off friction, and I'm just going to leave it on my acrylic. So in here we can see it has defaulted to 1150 newtons per millimeter is my stiffness. This is, and if I wanted to change these, I would just turn off my material and be able to type them in. My exponent is squared function, and this is my maximum damping. So when a penetration of 0.1 mil occurs, the damping will no longer increase any further than this maximum damping. That's what it means. Okay, so let's take that and we're going to run it. In fact, I'm going to actually run it twice as fast. And we're going to run it twice as long. And if you're having difficulty dragging these to the right place, you can right-click and edit them, type them in manually. And we're going to calculate. Okay. So as we go through, we're going to look. Going to take a look at our impact at the top. Let's just go normal to it. We can see it's a little bit coarse, so I'm just going to increase the frames per second to 50 just so it's a little bit less jagged. And what we can see as it goes around, we can see this impact and the amount of, as the force increases, it allows the impact to occur. And noting that quite a bit of penetration occurs at this point in time, and it actually has enough velocity to jump and carry on. Okay, so let's take a look at some of the results, and then we'll talk about what some of them mean. So we're going to create a new plot, and this time we're going to use forces, contact force, and we're going to have magnitude, and we're going to choose two components, and it will show me the contact forces between them. In our case, we can see, if I look at these, we'll notice that some of these have single points or just a couple of points. So these are our impacts of our 1, 2, 3, 4 impacts, and these single spikes need to be ignored. Okay. So the reality is that there's not enough points to be able to describe the force, because this is as it penetrated, it repelled, it went back out. This example here shows another series of peaks with really high impact forces. They need to be neglected. Zooming in on this area here, we can see that we have a series of points that describe a smooth contact, and these values can be extracted. However, the spikes need to be neglected. Oops. So back in our model, we could take this back down to say 50. So right click on the axis, we can change the scale, make the maximum 50 if we want. We can see we have some points that are reasonably smooth. And these contact forces at this point probably could be taken. Clearly not very much, 5 newtons, and that's probably because this part is not made out of steel or anything. So we're going to change it. Come back, recalculate. You can see obviously our force has gone up due to the increased mass and load on there. But these spikes still need to be neglected. And we can see where there's no contact occurring. Likewise, we could actually take this geometry and make something a little bit more realistic, like a rounded end, and then recalculate. And we'll have to redefine our point because it's been consumed. Okay guys, we're going to stop on there. We're nearly out of time, so we're going to review the last model really briefly, and then we're going to move on. So this example here is a container lifter. Sure, my animation's not working right at the moment, so we're just going to go straight to it. This example, we can see the container lifts and moves across as we see fit. So to make this model, we've basically built the model. I've modeled some of the entities, not as cables, but just as sketch lines, and connected points of sketches to other points. I have drawn a path that comes from the corner and up and onto the bed, and I've duplicated with a derived sketch the same for the tip. So my first study is set up in a very similar fashion. However, we have made a pathmate motor, and we've taken the pathmate of this endpoint, moved it from the start to the end over 20 seconds. We can see the smoothed function. We've utilized a lock mate additionally to the other, so these two components are locked together, so they will move as one. I then created a series of reaction forces for our joints, and I've also created, we can see here, a displacement plot between these two blue points that describe the distance in my cylinder. So looking at these plots show me the distance of the cylinder to achieve the motion that I wanted, and these can be saved as CSV files by right-clicking and utilized later. So I've done one for the top and one for the bottom. This example pulls in those precise curves and reapplies them, so it really achieves just the same motion, but by moving the cylinders. So we can get forces and powers for each of the linear motors based on the movement that we've chosen. As you can see, motor force here. So we've got 120 kilonewtons of force. Next, I utilized another study. Instead of doing the linear motors with a data sets, what we've done is utilize segments. So these segments, you can see I have say start and go between 0 and 4 seconds and move 400 mil So if we keep this linear, you'll see 0 to 400. And each of these is actually creating a linear interpolation between them. And if we didn't want the middle one, we could even delete that and say just go straight from here to here. In fact, or the other one, we could make it much smoother altogether. Cool. Let's recalculate those. They can be saved out to external files as they have here. We'll get an idea of what we've changed. See, our movement's quite different. And if we change the interpolations, you'll see more jerk and other things occur. Okay, we're about out of time, so we're going to wrap up the webinar. Some of the other topics that we might discuss and other events would be creating motion loads with the expression to link things. I have an example which I like to use, which shows a bowling ball, and I've applied two forces to it that change based on its velocity. These are to represent the rolling resistance of the ball. Likewise, air resistance, forces on cylinders, and other mathematical functions can all be input. So you can base it upon the actual measured event that you put in there. Event-based motion allows us to put servos and lasers and sensors and make motors start and stop and change based on things happening in your motion study. And we didn't talk about bushes and flexible joints, but for those hinge joints and other types of joints, they are perfectly rigid, and if we want them to move or be able to take load, we need to add flexibility to them. And in the same sense, sometimes we end up with redundancy in those degrees of freedom. If we have a door with 8 hinges on there and they're all perfectly rigid, you actually only need one of them to be able to describe and remove the degrees of freedom. So the others will not attract a load. And finally, these results could be exported to FEA. Oops, let me get rid of that. So thanks for listening. We talked a little bit about what motion simulation was, the interface, adding loads, forces, motors, bodies, results, motion function builder, cam synthesis, contact, and a quick overview of further topics. So I have a few questions, and thank you for listening.